So we're going to look at free body diagrams, and we need a body on a table. So we get a body with a mass on the table, so we'll use a book called mass, obviously, and we put that on the table. Okay, we're going to draw it. So that's the body, and now we must add in the forces. Okay, so the first force you always add, unless you're not on planet Earth or you have no mass, and it won't be working then as a free body diagram. The one you always put in is the force of gravity, and it's vertically downwards. Force of gravity always goes in first. Vertically downwards, label it W, weight. Okay, or you can label it Fg if you like. Then you look at it and you say, okay, this body is at rest, so there's no net force in the vertical direction. Okay, there's no net force in the horizontal direction either, but we haven't put in a force. But we have put in a force in the vertical direction, so therefore there must be a second force equal and opposite of the first force. Okay, so a force straight up, and that force is being provided, of course, by the table. Okay, and we normally call that, the reaction R. Okay, you can call it force up if you like. We normally call it the reaction R. Alright, so we're still in business. That's it, done. Now let's take case 2, where the body isn't at rest, but it's moving at constant velocity. So I'm applying a force to the left, and it's moving at constant velocity. So I have to put in the force applied to the left that I've applied. But okay, in the vertical direction now, the vertical direction is sorted. In the horizontal direction, it's traveling at constant velocity, so it's still not accelerating, so there's still no force. Remember, force is what causes acceleration. There is still no force, so there must be another force in the opposite direction of equal magnitude. And there is. Okay, and we know that that's caused by the frictional force, and we put in FF. Now, to be absolutely sure, you must make sure that it's clear that R is equal to W, it should be from your diagram, and that the force applied is equal to the force frictional. I would put that in over here as well to make it sure to be sure. Okay, so there we go. Let's take the final case that you'd have in a situation where we have a horizontal table where the object is actually accelerating to the left. So here we go. Right, the object accelerated to the left. Okay, so in this case there is a net force to the left. Now there's still a frictional force to the right, but the applied force to the left must be bigger. So we make that clear by the diagram, make it very clear, and the applied force is bigger than the frictional force, and you put it in like that. So there are all the cases for the body on the table. Now let's take a second situation where we elevate one side and turn it into a ramp. So we've turned that into a ramp now, and we will redraw this. Okay, so our body is now, okay, so that's our ramp, and the body is on the ramp like that. Okay, where's the body gone? So the body is on the ramp, and it's at rest. Okay, so in this case we have a force of gravity down, but that is now vertically down again. We have a reaction up. Now the reaction up, okay, it's going to be there. It's a bit more difficult for you to figure out which is a bigger arrow. For the time being, we're not too worried about that. And there's also a frictional force up. Okay, and the frictional force up, the combination of the frictional force up and the reaction should be equal to the weight down because it's at rest. So in the vertical component of the two of these added together should be equal to the force down. And there it is. That's the vertical component, and it should be equal to the force down. Okay, but you wouldn't be drawing that in if you were asked for a free body diagram. You'd just be drawing that in. Okay, we'll come back to more of them later, but they are the core ones. Okay, now one or two others to keep track of. One that came up in your homework the other day is centripetal force. Remember, if a body's moving in a circle, okay, so we had a situation of a body moving in a circle. So let's say a body is just going in a circle like that in a vertical plane, a bit like what we had, right? Okay, this body has a mass, so you always put in the force down. Okay, force of gravity. But remember, if it's moving in a circle, there is always a centripetal force towards the center. Always towards the center, no matter what. They'll be the two forces. You could have put in another force, a reaction up due to the air or something like that, or the hand, but they were the critical two forces. But if it's centripetal force, always a force towards the center. If you have a string, let's say this is a pendulum moving, okay, there's always a weight vertically down, And in this case, there will be a tension in this direction along the wire. Okay, there will be a tension along the wire. You can resolve that tension into components. We'll be dealing with that later. But that's the free body diagram that you will be drawing. Okay, free body diagram, straightforward. Usually forces, they could ask you others. They have asked you in the last year others. In other words, put in a velocity or acceleration. Same idea. You decide what you're putting in and you draw your arrow and you label your arrow. If the arrow is unlabeled, you could be in trouble. Never leave a diagram or an arrow unlabeled. Just not something to do.